Okay. So let's start. So last time we learned about linear regression. Basically, we want to predict one variable from another one. Today we are going to predict a variable from another variable, but it's in a different way. And the technique that we will learn today is about decision tree. All right, so the outline for today, we will learn about variance measure and also different type of algorithm. For decision tree, the main algorithm is Hunt algorithm. The rest of the algorithm are an extension from Hunt's algorithm. And some of these keywords you may have heard from different field like entropy you may have heard in chemistry or physics. We will see how uh, a computer scientist use entropy to help with the learning. So what are the problems that we are trying to solve using a decision tree? So a decision tree is a method, is a classification model. Basically, you define a rule, right? You define a rule for classifying data based on uh, testing data, right? Based on a lot of attributes. So in computer science, when we talk about tree, the tree consists of vertex and edges, right? So we have vertex and then we have some kind of edges. Now, for the tree, at the top, we call it a root node, right? It's a root node. And then the node at the bottom, we call it a leaf node. So basically, a tree in computer science is an upside down tree. So you have root at the top, and then each of the node will point to its children, right? So this relationship called um, children, right? So they have a children, and at the end, at the bottom, the node that do not have children is called a leaf node, right? So it is like an upside down tree. How do we use this structure to help with the classification problem? So basically, for any non-leaf node, right, we will call it a decision node, right? So the node that do not that have at least one children uh, is called decision node, and this decision node will have attribute and value associated to this node, right? For example, if you have uh, something like this, right? You have outlook, meaning the weather today. What is the weather today? And if the weather is sunny, right? So basically the decision node is a node that asks you a question, and you have to and you should be able to answer this question based on the data, right? So you look at the outlook, and what is the weather today? You have sunny, overcast, and rain, and depending on the answer, you go down the tree, right? You go down to an age that corresponding to your answer. So in the example, you want to know whether or not you want to go out to play tennis or you want to stay home. And the decision will be yes, I go to play tennis, or no, I stay home. So this decision tree will help you decide what is the best action you should do. So first, it look at the weather. If the weather is overcast, then you always go, something like this. So we have decision node right here, right? We have decision node, and then the leaf node, right? The leaf node is will produce the result. Basically, all the leaf node in decision tree is a decision. It's the action or the answer that you want to know. Actually, uh, let me download the driver so I can write better. It should take a couple of minutes because they change they change the computer every time, so I have to like re-download the driver every time. Okay. So we have decision node, and then we have leaf node that produce the result. It's basically tell you like which class this data belong to. And our question is, how can we build a tree, right? How can we build a tree like this? Because our data have many attributes, right? And what would be the first attribute? How do you pick one attribute from the others? Like, what is the best attribute to pick? So there are many questions before we even begin building a tree, because we have many choices, and the choice actually matter, right? Sometimes you want to check the humidity first, or you check the windy condition first, or you check the outlook first. So whatever you pick, it actually affects the entire decision. So this is another example, right? So I have this unlabeled data, like I have flamingo, and I want to give it a class, and my data have like body temperature, warm, that is give birth, and the answer is no. So we have this kind of decision tree, and we can use this data, right? We can use this decision tree with the data to infer the class. So we have body temperature, we have the answer is warm. So we go down the edge that's called warm, right? So the edge is the answer of the decision node question. And when you go to warm, you have another question that is give birth, the answer is no. And when you have no, you have your answer is non-mammal. And so you predict that this data is non-mammals. So far so good, right? For the decision tree. So it's a tree of decision node and then the answer at the end. Now you can have the data that is non-categorical, right? For example, you have two classes. You have circle and then you have triangle. And this circle and triangle lie in like two-dimensional space. So each data have two attributes, x and y. And the x and y can be real number, right? So from here, we only have category, right? You answer one way or the other, and the answer is infinite answer. But for here, you have a real value, right? For example, this data, it could be like 0.12 and then 0.9, something like that, right? X and Y. And then when you have new point, right? Let's say you have point right here, right? You have your new data. So what should be the shape of this new data? Is it circle or it is triangle? What do you think? Is it circle? Like, is it around here? Is it circle or is it triangle? Right? If you look on the left side only, like if you don't look on the right side yet, you look on the left side, right? You can see, oh, this one maybe is close to circle, right? So maybe it should be a circle, right? So that is your instinct. Now, in the decision tree, we need to make a decision, right? So perhaps you start with attribute x, and the question you ask is x greater than 0.43? And depending on your answer, yes and no, it's going to continue the path, right? So basically what it does is that you have this vertical line right here, and this line is x equal to 0.43. So this is the decision tree actually split the space into two parts, right? Yes and no. So the yes is on the left side, like the left is less than, right? So this is the left side, and this is the right side, right? So it split the space into half. And then, well, for this data, we have x is greater than 0.43, right? So we actually go to the no, no. After you use x, right? You have, so you only look at the data on this side. You only look at the data on the yes side. And we can split this data even more, right? So we have our second decision node. This node asks you, is y less than 0.33? So you have this line, right? Y equal to 0.33. And you want to split the right part into two smaller area, right? So we have the yes side with less than, and then the no side with greater than, right? So because your data have two attributes, it is common that the number of decision node, if you go down the tree, should not exceed the number of attributes you have, right? You don't want to split x again, like after you already split x one time, or you already split y for the first time, and so you want to start giving the answer after you split every attribute. So if you look at the yes side, right? If you look at the yes side of the y less than, how many data is in y less than 0.47? No, less than 0.33. You have to 3 data point, right? You have 3 data point, and all the data point are circle. So basically, when you go down to this area, you have 0 triangle and 3 circles. What about the node side? In the node side, you have like 1, 2, 3, 4. You have 4 triangle and 0 circle. So when I have my new data over here, right, it start at the root node. Is x less than 0.43? No, right? So you go to this node. Is y less than 0.33? No. So you go down to this node. So our new data is in this area. And in this area, what do you see? You see 4 triangle. And when you see 4 triangle with 0 circle, what is your decision? It should also be triangle, right? Because in this area, you only have triangle. So your new data is in this area, so it should be the same as everyone, right? So basically, when you go down to the leaf node, right, you go to the last area, you just answer the class that are majority, right? So in this example, right, we have our data scattering around. And when you come down to the decision tree, each of the decision area actually only have one class, right? So this is our ideal situation to be able to split the space such that at the end you only end up with one class, right? Because if it only have one class, you would have a very high accuracy, right? Because a lot of the data, right, are concentrated in this area and they are agree on the same class. So this is what we want, right? We want to split the data set based on the attribute so that each set only contain one class. That is the final goal, right? Whether we do it or not, we don't know, but that is our goal, right? Our goal is to split the data. So let's suppose I have this decision tree, right? I have the attribute A, B, and C. And at the end, right, I have my decision, right? If A is 0, B is 0, I answer plus, right? A 0, B 1, I answer minus. So the question is, what is the training error and the validation accuracy for this decision tree? Right? So this is the ground truth, right? This is the ground truth, right? It's basically the correct answer. But you have to use your data with the decision tree to get the prediction. So in step 1, what is the prediction? What is the prediction for data number 1? Is it plus or minus? So A 0, right? You go to the left, and then B is 0, so you get plus, right? So your prediction would be plus. What about number 2? Right? A 0, B 0 still plus. What about 3? Right? A 0, B 1, you get minus. So you also get minus. Now you go to A 1, right? A equal to 1, you go to the right side now, right? So when A equal to 1, you look at the C, right? If C is 0, you get plus, right? If C is 1, you get minus. So what is the training error? What is training error? So you have 10 data set. How many did you got wrong? 3, 4, 5. Is it 5? Right? So 5. Right? So you get 50% error. What about validation set? Right on the bottom. Let me move this. Can I actually hide? Okay. So for the validation set, right, I have 5, right? So for the validation set, right, I have 5. So when A is 0, I look at the B, right? So B0, I get plus. B1, I get minus, right? When A equal to 1, I look at the C value. So if C is 0, I get plus. If C is 1, I get minus. So for the validation set, the accuracy is 405, right? So it's 80%. Right? So when you have decision tree, it's very easy to make a prediction. Right? You just look at the attribute at the node, and then you look at the value, right? And then you pick the size corresponding to the value of that attribute. Right? So if the attribute is category, if it's a category, then you would have the value on the edge. So if they are maybe if it's like 0, 1, 2, then you will have 3 branches, right? So you have like A from 0, from 1, from 2, right? So if you have like three value on the categories, if it's a real value, right? If it's a real value, your decision node is going to be a condition, right? It's going to be a comparison. Like for example, that we have from last slide is like x less than something, and the edges is always going to be yes and no, right? So for real value, the decision node will be condition, and then the edge will be yes or no. For category, the decision node is going to be the name of the attribute, and the edges is going to be the unique value of each possible outcome. Okay, so how you review a decision tree, right? So there are exponentially many decision tree, because let's say you have an attribute, right? Like your data have an attribute. How many ways you can pick your root node, right? So there are n way, right? Because each attribute can be the root node. And after you pick the root node, right? How many you can pick for the next one? It n minus 1, right? You have n minus 1 attribute. So you go down, the number keep multiplying, right? The number of possible tree you have like n times s minus 1. So it's at least n factorial. And not all the trees are the same, right? Some trees are more accurate than the other. And we can evaluate it, right? Because we just evaluated it just now, right? If we have the tree, we can check the accuracy, right? That's very simple. So finding the optimal tree is computationally infeasible. So you will never find the tree that gives you the best accuracy. But that does not prevent us from building a tree. So all of the tree, decision tree algorithm is going to be based on heuristic, right? There is no optimization, because we already proved that to be able to find the best answer, you have to try exponentially many solutions. So there you have to come up with some heuristic. Not only a heuristic is easier to do, but it's also more efficient, right? You don't want something that take a long time to compute. So the decision tree you have is going to be always be suboptimal, right? Always be suboptimal. And even though it's suboptimal, you still have to come up with a way to compare two trees, right? How can you pick one tree from the other? Of course, you're not going to try every tree, but maybe you pick a few class of tree and then you just log on into the decision. So we start with Hunt's algorithm. This is the very first algorithm for decision tree. Now, Hunt's algorithm is a greedy algorithm that recursively build a decision tree. And let's say DT is the set of training record at node T. So what does it mean, right? It means that let's say, for example, this data, right? For this node, when you look at this node, you look at all of the data, right? You look at all the data. When you look at B node, because you only look at A, and then you make a decision based on A equal to 0, right? So dt here is going to be from 1 to 10, right? But for node B, dt for node, actually let me make this one easier. So basically the data at node A is going to be everyone. The data is node B are the data from when A equal to 0. So for B, you only look at 4 data. So basically you split your data set, right, at node A. And when you go down the tree, you only look at smaller set of data. So that is the definition of DT. So the first step, right, if all the record in DT belong to the same class YT, then T would be a leaf node, right? So we arrive at this situation, right? So basically you are at this node, and the DT of this node have only one class. And when this node only have one class, you declare it a leaf node. You don't have to go anymore. You stop here, and then that is your answer, right? So this is a simple case, right? All the DT are in the same class, that's the answer. But if it's not, what would you do, right? So when the answer is not so clear means that in the DT, you have both class set or you have many class set, and you are not sure which one should be the answer. It means that you should split more, right? So we have to select attribute test condition and partition the record into smaller subset, right? So basically we just pick some attribute, and attribute is going to be the decision node. And based on this decision node, you are splitting the data again into two parts, right? And then you repeat the same process again, right? You check step 1 and step 2 again for each of the smaller data set. Okay, let's work on the algorithm with the example, right? So I want to predict if a borrower will pay back the money. Basically, I give out a loan, right? And then my client will borrow money from me, and I keep track of the data, right? For example, does he have a home? Is Are they single? How much money do you make yearly? And this would be the class that I want to predict, right? So this is like you never pay back, and this one is like paying back. So I want to make a decision tree so that when I see a new client, I can use this decision tree to predict whether or not my new client will pay back the money. So your default, right? When you start at the root node, right? Your first iteration at the root node, your DT would be everything, right? From 1 to 10, right? So if it's 1 to 10, if you want to make this the answer without checking, what would be the answer? Right? You look at the majority, right? We have 3 yes and then 7 no. So the default answer is no. They'll never pay back. But it's not so clear, right? Because 3 of them pay back and 7 of them doesn't pay back. So when this is unclear, like all the data is not belong to the same class, so we have to pick some attribute. So let's say we pick homeowner, right? Let's say we pick homeowner. We pick the first column. So the first column, we have the homeowner. So this is going to be my decision node, right? This is binary, so you only have to write the name of the attribute, and then the edges that coming out is going to be yes or no. So for my client who have a home, right? Who have a home, what is my DT? So I look at the yes, right? So I have 147, right? So this one is 147. And on the right side, right, my DT is equal to 2, 3, 5, 6, 8, 9, 10, right? So I split my data into smaller set based on one attribute. If I stop here, right? If I stop here, what would be the answer for the left side? Right? So I look at 147, right? So 147, all of them say no, right? So for this side, I can strongly say no, because everything, right? Everything in this side have the same class. So this node is going to become a leaf node, right? Because everything, right, you have no, no, and no, right? So everything become no. So this one become a leaf node. So on the left side, you don't have to expand anymore. You stop here, right? So stopping here is the right decision. What about the right side? If I were to give the answer for the right side, what would it be? Right? So 2, 3, 5, 6, 8, 9, 10. So I have 3 yes and 4 no. Right? So this side I have 3 yes and 4 no. So it's not clear, right? This side is not clear which I should answer. If I answer for the majority, I would say no, right? Because no is more than yes. But because they are not one class, I have to split this one even more. So I try to split with the second column. right? I try my second column because I already tried first column, so I will not go back to the first column again. So I pick the second column. I pick marital status, and it's a category, right? And the way that you split the category, you can split like one by one, right? You can split um, to be like single, divorce, and then married, right? You can split like this. That's perfectly fine. Or you can group them and you split into two sides. In many algorithms, they prefer to split into two nodes. It's easier to visualize, and it's easier to do some computation when they are at a maximum of two nodes, right? So ideally, we just want to split into two sides, right? It's easier to deal with than three sides, right? In a very rare case, you would go for like many branches, but if your tree is very large, right, having uh, a lot of split decision will make your tree even bigger, right? And then it will slow down the decision making process. So here I divide into single and divorce, basically not marry and marry, right? So that's what I pick. So for single and divorce, what is my DT? What is my DT for single and divorce, right? So that person does not have a home and single or divorce, right? So I look at all the no and single divorce. So I have this one, no divorce, no single, no single. So this side I have 3, 5, 8, and 10, right? And this give me 3 yes and 1 no, right? Give me 3 yes and 1 no. Now for Mary, right? So for Mary, what is my DT? So my DT would be on the one with no or honor, and then the marital status would be Mary. So we have number 2, right? Number 2, number 6, and then number 9. Oh. For homeowner is yes. So yeah, the yes is already here. So we only look at the no one, right? So we only have 2, 6, and then not 2, 6, and 9, right? And 2, 6, and 9, all of them are 3 no, right? So that means that for this node, right? For this node, everything are the same class, right? Every data is the no class. So this node is going to become a leaf node, right? Got everyone agree. There's no need to further break it apart. On the left side, right? On the left side, you have 3 yes and 1 no. Basically, it's almost yes except one person, right? Almost yes except one person. So you can split this even more, right? You can split this even more, right? So let's say I split. So I have 3, 5, 8, 10, right? So dt here is 3, 5, 8, 10, right? Yeah, 3, 5, 8, 10, and this give me 3 yes, 1 no, and then I split it even more. right? That's my last attribute, right? My last attribute is the annual income. And the annual income is a real value. So when it's a real value, we actually have to make compare the value in for some constant. For here I pick 80K, right? You can pick any number. You can pick 100K, you can pick like 120K, or you can pick like 5K, right? You can pick any number for the comparison. Suppose I pick 80K, right? What is the DT for the website for the one that is less than 50K, 80K? So I look at 3, 5, 8, 10, and the one that is less than 80K are this one, right? So this one is only have 3, right? And then the right one is going to have 5, 8, 10. So I successfully divide 1 node and 3 yes into each of the node. So when you reach this state, right? This one only have 1 data and it's a node. So this become a leaf node. On the right side, you have 3 yes, right? You have 3 yes. So this one is going to be the yes node. So that is how you build a decision tree, right? You pick the attribute, right? You make a test condition, and then you split the data into 2 smaller sets, and then you recursively go to each set, right? Whenever the set contain only 1 class, that is what you stop, right? You stop there, and that is your answer. If not, then you repeat the same process. You pick the next attribute, and then you split them. So that is the Hunt algorithm, right? So for Hunt algorithm, he doesn't tell you which one to pick. You can pick any attribute at the start. You can pick any value for the comparison. It just happened that the way I pick it cleanly divide the data, right? Sometimes, even though you split the data using all the attribute, you will end up with a mixed class. Then you have to accept the majority vote for that mixed class. So Hunt algorithm will work if every combination value is present in the training data, right? What does it mean? It means that if there are more than 3 marital status, right? For example, there are a new status coming up in your test data, but it's not in your training data, then there's nothing you can do about it, right? For example, if I have unsure, maybe unsure, right? I have the new status unsure. If I go to here, when I reach this node, right? This node is mature status. You go left if you are single or divorced. You go right if you are married. But if you are unsure, where do you go? You cannot. So it means that in your training data has to be quite complete, quite exhausted. Every possible value of each attribute that are not real value must be present in the training data. Otherwise, you cannot predict the testing data. So that is one thing to note. Now, there is also possible that if a child node created in step 2 contain no record. So what does it mean, right? It means that, let's say, when I create, let's say I pick this one to be like 800K, right? This one to be less than 800, and this one is greater than or equal to 800. What happened is that all the data will be on this side, and this one will be empty, right? So what happened in this situation is that a leaf node is created and it takes the class of the majority class in the parent node. So even though this one is empty, it's going to become a leaf node because you cannot split it even more because there's nothing to split, right? But what is the decision? So the decision will take from the parent. So the parent here, um, if they are more yes, more no than yes, then this leaf node will answer with no. It's going to take the majority of the data in the parent and it will answer in this node. Right? This for the case that when you do the split, it just happened that all the data is on the one side and the other side is empty. So another condition is that if all the record in the DT have identical attribute but different class label, right? So basically there is a duplicate, like there is a duplicate data, but the the class is different, right? The class is different. Then you will also stop here. You declare it's a leaf node, and you take the class label for the most class of the record in the DT. Right. So because every time when I make a leaf node, I would pick the majority class, right? I always pick the one that has the most common in that group, in that set. It means that if I ever come to a situation where two classes have the same number of data set, then I would be in trouble, right? For example, if I split everything already, and at the end, I have like 40 yes and then 40 no. They just happen to be equal. So if I come up with this situation, it's going to be hard for me to pick whether or not I will answer yes or no because they have the same number of attributes. So when you think of this situation, it means that whenever you split the data, if the smaller group you split have equal number of class, it's actually a bad split. You don't want to split a class that when you go to the smaller set, both sets have the same number of class. You want a bias. You want one class to be dominating the other class when you split the data. So with this in mind, you can actually compare the split, right? Like if I have, uh, like let's say I have two split, right? This one split into like 3 yes, 3 no, 2 yes, 2 no, and then this one is like 4 yes, 1 no, and then 1 yes, 4 no. Which one do you think is better? Right? You would think the right one would be better because when you split the data, you can almost make a prediction for the leaf node for the next step. But on the left side, everything is still unclear. You have the same number of classes in two sets, so the split is not as good. So the question is, how can we measure the split, right? Intuitively, we know the left side is bad, the right side is good. but we need something more mathematical, right? We want to be able to compute some value, and then you compare two value. Oh, this value is higher, so it's better, right? You want some guarantee, right? It's not just some like your instinct, right? Because you want to tell a computer to learn the decision tree for us, so we have to make a formula for it, right? A formula to measure how good your speed are. So this become our main question, right? What attribute should be chosen first? And another one is, when do we stop? Now, in Hans' algorithm, when do we stop? We stop when all the data are in the same class, or you already split all the attribute, right? That is the stopping condition for Hans' algorithm. But let's say your data have like 100 attributes, right? You want to split 100 times, that's going to be a very big T, right? Because one split, you have two nodes. If you have one split, you have 2 to the 100 node, right? So you have a lot of nodes. So perhaps you should stop early, right? So there a trade-off between stopping too early or stopping too late, right? If you stop too soon, right, it's gonna underfit the tree, right? Basically, you haven't explained the data very well, and you already stop. If you stop late, like you build a very large tree, like you wait until the last minute to stop, it might produce overfit tree, right? You overfit the data, right? So basically, you just bias to the training data. So you want something in between, right? You don't want to stop too soon, and you don't want to stop too late. So in the early day, all the algorithm for the learning, they have a stopping condition, right? And most of the stopping condition would be like if it's an optimization problem, you look at the gradient. If the gradient is less than some epsilon, some small value, then you stop, right? But for a modern optimization, you just look at the number of iteration, right? Or epoch, right? So before, like for example, like if this is accuracy and this is the time, right? The more you train, you have the better accuracy for the training data, right? And it's going to stop somewhere, right? So the time here, sometimes you want to fix the time, or sometimes you want to have some criteria to stop. And if you stop too late, right, it's going to perform very well on the testing data, but on the train on the it's going to perform well on the training data, but not well on the test data. So let me remind you that the assignment is due today. For those of you who haven't submit, um, you should probably already see the leaderboard, right, for each submission in the Kaggle. So some of the lower rank in the public actually get like number one in the private. So you have two choices, right? So you make use of the two choices to use for the private dataset. Okay, so let's start with the attribution test, right? For binary, right? Binary is always generate two outcome. right? The binary attribute always generate two outcomes. For category, you can have more than two split. You can have like multi-way split, or you can group them, right? You can group them. Sometimes the order matters, right? For example, if you have the shirt size, right? You have S, M, L, XL, right? So when you split into, you want to basically you want to find like the split, like one of these split, right? And then one side would be SML, one side would be XL, right? You don't want to group S and XL together and then M and L together. You want to preserve some order if you want to group them. Now for continuous value, you have to pick a constant, right? You have to pick a constant and then you split into two. Now you can also do multi-way split for attribute in range. In range, like for example, if you only look at annual outcome, you can say like less than 10K, from 10K to 25K, from 25K to 50K, right? So there are two strategies for uh, a continuous value. Now, in most algorithms, you would prefer the left one. Basically, everything should be binary because it's like more compact. And when you split a lot, right? When you split a lot, you have to make sure that like each of your split is actually good, right? Otherwise, is a ways to split in many ways. Okay, so all of this split, now we can move on to the measurement, right? So basically, we have every attribute. We try to split based on each attribute, right? So if you have 100 attribute, there are 100 ways to split them. And you want to score each split, and you pick the best one. Now, there are many measurements. There are entropy, you have a Gini index, also information gain. So all of these measurements will tell you, will determine if one split is better than the other. So all of these attributes is actually measured in terms of class distribution before and after split. So basically, when you do a split, right, you have dt of the parent, and then you have dt of the children. So the measurement here is going to take all the three values and compute the score of this split. So let's start with some notation, right? So when we talk about class distribution, basically we just look at the ratio, like for each class. Like for example, at a node T, Pi, basically we say Pi, is the probability of the data being in class I. So if I look at the root node, right? So let's say if I have the node with home owner, right? And then it's gonna split into yes and no. So for this one, what is, so let's say no is 0 and then yes is 1. Right? So I can write. So the distribution, right, for this node is going to be P0 and P1. And P0 is the fraction of the class belong to class 0, right? For this one, how many is 0? There are 7 0. So you have 0.7 and 0.3. So this is the distribution for the node homeowner. Now, after you split, right? After you split homeowner to yes and no, right? On the yes side, what is the distribution? So on the yes side, right, I only look at these three, have 3 no. So it's 0, 1, right? Oh no, it had to be 1 0, right? 1 0, right? So 100% is no, and then 0% is yes. What about the right side? What is the distribution? Right? So we have 4 no and then 3 yes. So it's going to be something like this. Okay. So that is the distribution. Right? So we have distribution of the parent, distribution of the child node. So we're going to go to the ID3 algorithm. So we have this card distribution, and of the algorithm is going to use this value to compute the score. And we will learn about these 3 algorithms that give different way of scoring. Right? So we have ID3 scoring system, we have C4.5 scoring system, and then we have card scoring system. So let's look at the ID3. So ID3 is like the first version of the scoring system. It's actually like come out maybe a few years after Hans algorithm. So the measurement, right, it have the impurity measure, right? The score for this algorithm is called impurity. So when you think of the impurity, you think of like a jewelry, right? A very expensive jewelry should have a high or lower impurity, right? So impurity means there is some noise in there, right? So for a jewel to be expensive, they have to be very pure, right? Very pure. So the impurity score has to be very low. So they want to measure the impurity as well. So how do they compute the impurity? They use what is called entropy. So the entropy is a measure to create the homogeneity of a sample, right? And it actually measures the degree of impurity. So if you have number between 0 and 1, right? So the impurity of 1 would be very bad, right? It has a high impurity. And then if it's 0, it is very good. So in our case, what distribution should give me the worst possible impurity? What should this distribution look like? equal, right? Like if two classes are equal, it's very hard to make a prediction. So if it's 0.5, 0.5, it should give you impurity of 1, right? So the equation for entropy is the probability, basically the fraction, right? So this is the pi, the fraction times the log of the fraction, and then you sum over each of the class, right? For example, you have two class, you have like p0 log p0 plus p1 log p1, right? And after you sum, you take the negative. Why do we need negative in the front? Because when you take a log of a number less than 1, you get a negative number, right? But our impurity, we measure is a positive number. So we put -1 in front so that it's cancelled out. So let's see if this equation actually give us what we want. So 0.5 should give us 1. Which distribution should give us 0? What is the best possible outcome? It's going to be either 0, 1 or 1, 0, right? 100% is in one class. That is the purest form, right? The purest data set. All the data are in the same class. So let's try this one. So we have class 0, class 1, right? Let's say I have 3 different split, right? The first split is N1, the second split is N2, the third split is N3. And these are the distribution that I have. So if I have 0 and 6, right? My entropy, right? So this is the P0, right? My P0 is 0, my P1 is 1. So this is a perfect scenario, right? Every data is in class 1. So when I do the calculation, I have P0 is just 0. Log of the 0 is, what is log 0? What is log 0? It's actually undefined, right? Because in the log case, right, log 0 is going to go to the negative infinity. So in this case, right, the first term, it actually becomes 0 because of the of P0 having. So when you take the sum, right, if there is no class, like you don't even put in the sum, right, because there's no record with class equal to 0. So especially this term is non-existent. And then in the second term, right, you have -1, right? The P1 is equal to 1 time log of 1. What is log 1? Log 1 is 0, right? So you get this one equal to 0. So the entropy is actually a good measure for impurity. If I have almost perfect, right? I have 1, 5, right? So basically it's 1/6 and 5/6, right? So the one is almost perfect. You only have one example, there's a class 0, and the rest is class 1. And the entropy score is 0.65, right? You can use a calculator to calculate all of this. What is the entropy of the last one? You have 3 and 3. So in our intuition is that if it equals split, it should be equal to 1, right? So let's see if it's actually equal to 1. So I have P0, 0.5. I have P1, 0.5, right? Equal split. So I take minus P0 log 0 minus P1 log P1. This is my entropy for this split. So if I substitute the value, I get minus 0.5 log 0.5, right? Minus 0.5 log 0.5. So what do I get? I get minus log 0.5, right? Right, I have 0.5 here, 0.5 here. So combine them, I get just 1, right? What is log 0.5? Right? So log 0.5 is minus 1, right? We take log base 2, right? So log base 2 of 0.5, so basically it's 2 to the minus 1, right? And then you put the minus 1 to the front. So you get minus log 2, 2, and then this log 2, 2 become 1, right? This one is 1, so it's minus 1. And we have minus in the front, so it's become 1. So the entropy is the measurement of impurity, right? If it equals split, you get 1. If it perfect split, you get 0. If it something in between, you get some number. So what you want is, you want the number to be very low, right? The lower the number is, the better the split. Okay. So now, how do we use entropy? So the entropy is defined on one node. And what I told you is that when we want to do the split, right, we have the parent node, and then we have the children node, right? Each of them have different distribution, right? Basically, we have 3 distribution. The equation for entropy, let us calculate one node, right? So we have entropy for this node. I have entropy of this node, and then I have entropy of this node. And I want to be able to combine all 3 to score the overall split. And so to do that, right, we're going to use what is called gain, right? So the gain or is the triangle here, right? It's basically how much impurity you can improve if you do this particular split. So the equation would be the impurity measurement of the parent minus the sum of the proportion of the data times the entropy of the children. So if I have this split, right, I calculate the entropy, let's say I say this node ABC, right? I compute entropy of A, I compute entropy of B, or C, and then entropy of B. And then I plug in, right? So it's basically entropy of A, if I use this equation, right, minus, it's going to depend how many data got split, right? So the number of data in B divided by the number of data in A times the entropy in B, right? Plus the number of data in C divided by the number of data in A times the entropy of C, right? So this is the gain for this particular split. So now you have a measurement for the split. It means that you can try many types of split and you compare the number. Now, this number, right, is basically the parent impurity minus the student, the weighted sum of the impurity of the student. So do we want this to be high or do we want this to be low? Right? So when we think instinctively, in the parent, you would think that the impurity would be low. The impurity would be high because it's a mix of many classes. And when you split, you want the student to be very pure. Right? So the parent have a high impurity, the student should have low impurity. So if you take the minus, the information gain, you want this to be high. Right? You want this to be high. The higher the information gain is, the better the split. Okay, let's look at some example. Let me go to example first. So I have the Simpson data set. Right? I have a person from Simpson. I have the hair length. I have the weight. I have age. And then my class would be gender, like male or female. And then I want to create a decision tree to predict the gender of my new character. Right? This character have 8 inches of hair, weight 290, is 38 years old. Is this character male or female? Right? So based on this data, I want to create a decision tree. So for this, I have 3 attributes. And have a decision to make which attribute should be the first one to test. Right? Now we have the measurement now that you can test each type of split. So I can start with the hair length, basically my first attribute. So the hair length, let's say I split with 5, right? Less than or equal to 5 or greater than 5. So at the start, right, I have all of this, right? I have how many person? 9, right? I have 9 person, right? I have 9 characters and the entropy, right? So the class split is 4 female and 5 male, right? I have 2 class, right? 4 male and 5 male. And so I compute the entropy of this node, right? The entropy of this node is 0.9911. So basically it's almost equal, right? For verse 5, it's almost equal. So the entropy is very high. Right? So it's basically like 4.9 and then 5.9, right, over 9. And after I do this split, right, the data is going to be divided into 2 sets, right? This is the child node, the student node. On the left side, right, for the hair length less than or equal to 5, I have 4 characters. And in the 4 character, I have 1 female and then 3 male. And so I compute the entropy of this side, right? So the same formula, right? Have 1 over 4 and then 3 over 4. And then I get 0.8113, right? 0.8113. And on the right side, For the hair length greater than 5, I have 5 characters, 3 female and 2 male. And if I compute the entropy, I will get 0.9710. Okay, you can use calculator later, but let's accept that these are the values. And I want to compute the information gain, right? The information gain is the entropy of the parent, right? So this one is basically 0.9911, right? So this is the first term. And then minus the entropy of the student, right? So 0.31, 0.81 on this one, 0.97 on this one. But the coefficient is the proportion of the data. On the left side, you have 4, so it's 4 over 9. On the right side, you have 5, so it's 5 over 9. Right? And then you compute this value, you get 0.0911. So this is the score of hair length split. Right? Right. So do you do all this for one attribute? Right? So you have the score, okay? And now you try, right? Because we just try hair length. Maybe we try weight, right? We try weight. Okay, let's say we try weight for less than 160, right? I just pick one random number, like 160. So using this split, I will have the weight of less than 160 and more than 160. Now, the entropy of the parent is the same as before, right? Nothing changed, so it's 0.9911. And then when you split using weight, right? The one that are less than 160, you have 4 female and 1 male. And the entropy of this group is 0.7219. On the right side, you have all male. So the entropy is 0, right? It's perfect group, right? Perfect group. So the entropy should be 0. And then when you compute the information gain, well, you start with the entropy of the parent, and then you minus the sum of the entropy of the children, right? So 0.9219 and then 0. And then because the left side have 5, the right side add 4. So these 5 come here, and then this 4 come here. And then you get the final answer to be 0.59. So if we compare this split to the hair length, which one is better? The hair length or the weight? The weight, right? Because the hair length, you only have 0.09. But for the weight, you have 0.59. So you have a better split. So you will pick this one over the hair length. Right? Let's try age. Maybe age might be better. We don't know. So we try age, right? Our last column. So we try age. Let's say I pick 40. Right? Let's say I pick 40. So age less than or equal to 40, and then the age that is greater than 40. Now for age less than or equal to 40, the left side, the yes side, I have 3 female and then 3 male. So this is like a perfect split, right? I mean, it's like 0.5 split. So the entropy become 1. And then on the right side, you have 1 female and 2 male, and then you have this entropy. right? So you have to compute entropy of every group when you do the split. And then the information gain you have is 0.0183. So compare this to the Helen. Which one is better? The Helen is better, but the best one would be by weight, right? So because we try all three, right? We try all the attribute, and then we found the best one, which is the weight. So we create, right, our first node, right? The first node is going to be split by weight. And the test condition on the weight. And if the weight is greater than 160, then your class would be male. Now on the left side, you have 4F, 1M, right? So you have to split this one further. And because you already split with weight, for this step, you have to try hair length and age, right? You have to try two. And it happened that the hair length is better. It can split into one male and then four female. Like this one would be the perfect split. And so you end up with this decision tree. So with this decision tree, right? So weight less than or equal to 160. If it no, you answer male. If it yes, then you check the hair length. If the hair length is less than or equal to 2, you answer male. If not, you can answer female. So this is how the ID3 algorithm works. You try all the attribute and pick the one with the best information gain, the highest information gain. So the next algorithm is C4.5. Well, it's a class of algorithm. There are many versions. I think the last listed version is the C4.8, and then we have the commercial one is like C5.0. So there are still ongoing research for this one. But in our class, we will learn about the most common one, the C4.5. So the C4.5, what changed? The change is numeric attributes, right? Because in here, when we split numeric, right? When we split age, we have to pick a constant to compare to. And the choice of constant will change the outcome, right? We change the split. So in IDT algorithm, it doesn't tell you how to pick. It's up to you to pick a number. Now in C4.5, they try to make the decision more smart, right? You cannot just pick any number. So what are the strategy for picking numeric attribute? So the way that they deal with numeric attribute, they look at the column, right? They look at the column, and then they sort the attribute from small to large. And when you split, right? For example, this is your data, right? 60, 70, 75. This is the data, right? Your sorted data. And each data you have class, right? You have class. And when you pick the split, you will pick the value between two adjacent values, right? For example, from 60 to 70, you pick 65. You don't want to pick closer to the number because you want the decision boundary to be far apart from the data. So you have some confidence value. So between 60 and 70, maybe you pick 65, you pick 72, you pick 80. And for each split you have, right? For each split you have, you compute some measurement, you compute information gain basically. You compute the gain of each of the split, and then you pick the best one. Like for here, they use a different measurement called Gini index, and we will look at the formula later. And they will pick this one would be like the best value, right? So you compute the gain for every type of split. So for numeric attribute, there will be many split. And if you have a lot of data, right? Let's say you have 1,000 data. How many split do you have to test? Is 1,001, right? It's between every data, and then before the first one and after the last one, right? So if you have more data, of course, you're gonna have to try more combination. So they want to make this faster. How do you make it faster? And the way that you make it faster is looking at the speed that happen between two different classes. So if you look at the data here, this split and this split are essentially similar, right? We have three nodes in a row. If you split it here or split it here, you split node into two groups. And you don't want to split node into two groups, right? You want node to be in one group, yes to be in another group. So the way that you do the split, you only split when you change from yes to no or from no to yes. If two consecutive numbers have the same class, you don't want to split them, right? You only split when they are in different class. So before we have, how many values do we have? We have about like 15, right? We have about 14. So originally we have 15 split, right? But if we only look at the split between yes and no, we only look at 1, 2, 3, 4, 5, 6, 7. So we look at the 7 split, right? So the number go down significantly. Right? So this is how the C4.5 algorithm deal with numeric value. It try all of the possible combination, but they try it in a smart way. And they kind of use different measurement, right? So we have the information gain, right? Right. So we have information gain, right, with the entropy of the parent, right, minus the sum of the weight uh, of the entropy of the children, right? So this is our information gain before. Now for C 4.5, they use information gain, right? So this is the same formula, right? So this is actually the same. The top one is the same. But they use a ratio instead. And the ratio, the denominator, it would be the split info. And the split info is given by this equation. Right? So this kind of like similar to the entropy of all the students combined, right? So in the information gain, you combine the entropy of the student, but you have a weight, right? So for children that have a large number of data, is going to dominate this term, right? For example, if I split into this one have like 100 data, this one have 3 data, right? The entropy of the 100 is going to dominate this term. But for the split info, right, you still have the entropy, but you don't put the weight anymore. So there are no weight in the front. So every child node is treated equally, right? And then you sum the split, and then you divide the information again. So again, we want information gain to be very high. We want the split info to be very low, right? So when you do the ratio, like you want the top to be high, the bottom to be low. So you want gain ratio to be high, right? So it's the same principle. You want a high value. So this is the extension of information gain, which is the gain ratio. So what is the gain ratio for attribute income? Okay, I have this example, right? So I have the data, collect age, collect income, collect student status, collect credit rating, and I want to predict whether or not they will buy my computer. So if I want to create, let's say I want to use income as a split, right? So basically I have income, and then there are 3 split, like low, medium, high, right? Low, medium, high. And this become the 3 set. So this become 3 set. When I calculate the split info, right? So if income is low, what is the split on here? What is the split for each one? So how many yes? 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 9 yes, and then 5 no, right? This is the at the income. What if the income is low? What is my split? So we have this 4, right? So we have 3 yes and 1 no, right? For the medium, I have 1 yes, 1 no. I have 4 yes and then 2 no, right? 4 yes and then 2 no. And then for high income, I have 2 yes and 2 no, right? So this is my split. If I use income, right? So 4, 10, 14. Okay. And I want to compute the gain ratio. So I compute the split info first. So for the split info, right? The split info, so this PV, right, compared to the entropy. So for the entropy, you only look at the data within the set, right? So for example, the entropy of this node, right? You're gonna have 3/5 times log 3/4, right? And then minus 1/4 log 1/4, right? So this is the entropy. Now for the split info, right? You have uh, three class, right? You have the three class. So V1 is the ratio of the record in the branch overall in the parent node, right? K is the number of branch. So the split info, right? This one have 4 data, this one have 6 data, this one have 4 data. So you have 4, this is the first one, 6, the second one, and then the third one is 4. So 4, 6, 4. And then the denominator would be 14, the total sum, right? So the split info basically measurement how balanced it is between each of the child node, right? And then you get some number. And then you compute the gain for the income, and then you take the gain of the income divided by the split info. So what is the gain ratio? So we have the gain for the income. This is fixed, right? Because the gain of the income, you only know how to split. Uh, if we split into low, medium, and high. So let's say we combine low and medium together into one group and then high in another group, right? So what is the split info for this one, right? So we have low and medium, right? If we combine them into one group, you have 10. So for this one, the split info for this one would be minus 10/14 times log 10/14, right? So this is the low and medium, right? This one is low medium. And then you have 4/14 times log 4/14. This is the high, right? And so you have a different split info. And then you can use calculator to compute, right? So I'm going to use Wolfram Alpha to help with the calculation. So what do I have? I have minus 10/14 times log base 2 of 10/14, right? And then minus 4/14 times log 2 of 4/14, right? And I get a number to be 0.8631. So this one is 0.8631. And now I want to compute the gain, right? So compute the gain. So actually for for the gain, it's going to be actually different value, but let's suppose that the gain is the same. But I mean, in reality, it's different, but it takes time to calculate. So if the gain is the same, right? This bits have a higher value, this bits have a lower value. So you want the one with higher speed info, right? Because when you combine 4 and 6 together, you get right. If you combine 4 and 6 together, you get 7 yes and then 3 no, right? But if you split, you get like almost perfect on the left side, and then like you have the yes dominate, like the more yes on this side compared to this side. So for this measurement, right, you can actually compare different type of split. So you pick the one with the higher gain ratio. So let's look at the last algorithm for today. It's called CART algorithm. The full name is classification and regression tree. So for this tree, they use Gini index for impurity, right? So in ID3 and then C4.5, you actually use entropy, right? Entropy for impurity. For class, they use Gini index. It's a different measurement for the impurity. And for car algorithm, they only use binary split. So only two split possible. So for this one is not possible in card algorithm. They only consider binary split, only split one node into two, but not more than two. What is Gini index? Right. So the Gini index at node T is 1 minus the sum of the pi of each class square. So in the entropy, right, in the entropy we have minus pi log pi, right? So here is basically 1 minus sum pi square. So this one, right, compared to the entropy one, is a little bit faster to compute, right? Because computing the log actually takes time. But if you multiply the same number twice, it's actually faster. So let's see how the speed we used to have for the entropy. So for the entropy, when we have 0.5, 0.5, the entropy would be 1, right? If it's 0, 1 or 1, 0, the entropy would be 0, right? So this is the case for entropy. Okay, let's look at the same distribution, but for Gini. What is the value of Gini? So for a perfect split, right, 0, 6, you have 1 minus 0 square minus 1 square. And then you get 0. So it's the same, 0, 0. Right? So the minimum value of the Gini and entropy is the same. Now, what about near perfect? For the near perfect, the Gini index, you get 0.278. For entropy, you get 0.65. So the entropy is a lot higher than the Gini. What about equal split? Equal split for entropy, you get 1, right? You get 1 for entropy. What about the Gini? So the Gini, you have 1 minus 3 over 6 square minus 3 over 6 square. What do you get? 1 minus 0.25 minus 0.25 equal to 0.5. So the entropy, the value of the entropy from 0 to 1, the value from Gini index is from 0 to 0.5. So they are different range, but the meaning is the same, right? The lower the value, the better. So let's say I have A and B split, right? I have A and B split. So if I split with attribute A, right? So the parent, I have 6 data of each class, right? The class 0, I have 6. Class 1 also have 6. So the Gini of the parent is 0.5, right? Perfect split. Let's say I pick attribute A and I split to yes and no, right? So this one, I will have the Gini of 0.486. And for B, I will have the Gini of 0.375, right? So how do I arrive with this number? For this one, right, I have node 1 and then I have node 2, right? I have 2 nodes, right? For node 1, I have the 40 split. So I'm gonna have like 1 minus 4 over 7 square minus 3 over 7 square. So this one would be 1 minus 4 over 7 square minus 3 over 7 square. So it actually understand that I'm trying to use the Gini index. Just give me the value. Let me refresh. So I get point about 0.49, right? About 0.49, right? 0.4. Let's try 3 digit. So 0.8, yeah, 0.49, 0.49. And about N2, right? So this is N1, right? For N2, I have 1 minus 2 over 5 square, 3 over 5 square, right? This one I should be able to do it by hand. So 0.5 is 0.4. This is 0.16. This is 0.6, so minus 0.36, right? And what I get is 0.48, right? So basically, the Gini here is the average, right? Basically, it is the average of the two, right? This one is the same, right? You take these two and then you take the average. And because the Gini index of the parent would be the same, no matter what split you pick, you only care about the Gini index of the children. So which one do you pick, A or B? B, right? You want to pick the Gini index that have the lower value. So you pick B. You can also do the same with uh, category, right? So you only need to compute the Gini index of uh, the class of the student, right? Actually, this one is the opposite, right? Spot is here, actually it's here, right? And then you just pick the Gini index that is the lower value. So for the Gini index, the meaning is the same, but the calculation become easier, right? You don't have to take the log. You only need to just multiply the same number twice. So these are all of the algorithm for making a decision tree, right? So once you have a decision tree, you can just save this and then predict anywhere else, right? So any question? Yeah, so the final goal of the decision tree is to make sure that you have the perfect split. And the way to do that is to have a measurement, and the measurement is the impurity. And then you have two choices. You have entropy or Gini index, right? So whichever choice you make, um, you probably have a different, slightly different outcome. Okay. So if if there's no question, then um, we'll take about 5 minute break, and then we'll come back to look at the code for the decision tree. Okay. Let's see. So decision tree. So for decision tree, the we can still use sklearn. Sklearn still have the decision tree. So first we want to load iris dataset. You use iris dataset for this one. So iris dataset, you can load it from sklearn, or if you create um, from in Colab, the sample dataset, I think, oh, it doesn't have iris. Okay. So I guess you will load it from sklearn. From sklearn dot dataset import the function called load iris. So this is the function. And then we can say our data frame equal to load iris, right? So if we try to print the df from the load iris, so what we have is still some data array, right? It's not the panda data frame, so it's not ready for training. So we have, so basically it have the attribute data, right? And then it have the attribute called target, right? So basically we have data and target. So we have to kind of like split them, right? So we can say x equal to um, df dot data, and then y equal to df dot target, right? And then if I can print x and y, then I have the data in one, and then I have um, the class, right? The y. So this y is the label. We have three label. We have label 0, label 1, and label 2. So in our example, right? In our example, we only deal with two classes, but in this data set, we have three classes, right? So for the equation, you have more term. Okay, so we have x and y, right? So we want to make a decision tree. So this x have I think four attribute, right? Four attribute, and then I want to predict y. So I want to make a prediction model, right? And before I have to make the prediction model, I have to always split my data into the training set and the train set. So I'm going to, I want to split the data into training set and test set, right? So I can test my accuracy. So again, we can get it from the sklearn. So we can say from sklearn dot model selection import 10 test split, and then we can say x train. I think x train, is it x test? Uh, y train y test equal to 10 test split, and then x and y, and then the test size. Normally I put pick like between 0.2 to 0.4, somewhere around that. And then I do random state equal to, let's say 42705, right? So when we run with the same random space, we will have the same training set and then the test set, right? And then I can print the shape, right? X train dot shape, and then Y train dot shape. So I know how many um, test or train data I have. So I have 120 train data, and I can copy this for test, right? So I have 120 and 30, right, for train and test. And now I want to learn decision tree. So I want to learn decision tree from training data, right? So I can say from sklearn.tree. So the sklearn have the tree. So they have the decision tree classifier, right? Because we want to classify based on the decision, right? And then we can say um, the model equal to the decision classifier, and then we can fit the train and test. For the decision tree, you don't normalize the data because normalizing in decision tree is doesn't matter, right? It make no difference because you only consider one attribute at a time, and when you measure the split, it doesn't matter if you scale or not scale, and it work on um, category data as well, right? For before we learn about linear regression, that's only work for numeric, right? Only number. But this one, if you have the column that are categorical, you can still learn, right? You don't have to drop that column. So after I fit, I can predict, right? So I have y predict equal to model dot predict x test, right? And then I can compute the accuracy, right? Basically, I can compute the score and then print the accuracy. So if I do this, I get 93% accuracy. Um, but we want to visualize the tree, right? We want to look at this tree because um, for the decision tree is the one of the the classifier model that you can visualize and understand how the prediction work. For other model is completely mathematics, right? You just multiply or plus number and you just add some coefficient. But for decision tree, you have a decision node and then you can um, actually visualize it. So we want to visualize, right? So basically we want to visualize the decision tree, right? So to visualize, there are actually many ways to visualize. Um, I think sklearn have uh, the method, right? So this one is the export graph width, but I will use the plot tree. And they have the for plot tree. And when I want to plot tree, I can just say plot tree and then I put the model in. So if I run the model, right, it's going to visualize the node. But I think it's very compact, right? So we want to use this in combination of the matplotlib. So import matplotlib as plyplot, and then you want to set up the figure size, right? And then when you plot a tree, you're going to have uh, more parameter, right? Actually, you can have the name, right? But because we don't have the name to begin with, um, we will skip that. If your data have the name of the attribute, you can put it here, and it will show you. Right now it's x2, x3. It means that the the third column, the fourth column, right, from 0 to 3. If you have name, then you can put name. There are few equal to true and then rounded. This for just visual. This for just visual, right? So if I plot like this, it's going to be look a little bit prettier with the color. So what happened is that if I pick x2, so the x2 is the third column. Like you start from column 0, 1, 2. So this is the third column, and it picked 2.5 and actually use Gini index. So this automatically tell you that it actually used card algorithm, right? And then initially you have the start at 120, right? And then we have this value 39, 40, 41. And when you pick this column less than equal to 2.5, you split into two groups, right? This one group only have one class, 39. So this one become a leaf node. So when you visualize this, the leaf node will have color, almost have color, right? So the white one means that you are not sure which class is going to be. For this one, right, you have 40 and 3. So it's almost class 2, right? Almost class, the second class. That's why the color it become almost green. You can stop here and just answer green, or you can just go more, right? You can go more. For this one, because we didn't set any parameter, it actually go until the value become pure, right? It will go until the value only have one class, right? Like this one have only one class, this one have only one class. So this is the decision tree that you can visualize and save for future. And if I look at the classifier, the documentation, right? The documentation. So you can actually pick the criteria, right? Between Gini, entropy, or log loss. I haven't told you the log loss, but it's basically entropy with different weight. But the default one would be like Gini or entropy. And then the splitter, right? Is it how you pick the split? Right? So basically, when you try different attribute, normally you will pick the best one, right? Pick the best Gini. So the default one would be the best Gini. But you can also just say random. It's going to pick at random from all possible attribute. You can also specify the max depth. So this max depth is also another stopping criteria. So in our decision tree that we have, right, we go down 1, 2, 3, 4, 5, right? We go down 5 steps. And at the very end, the data become very small. Like you only have 4 data sets, right? So when you have 4 data sets, it's actually not informative enough for you to make a prediction. Right? You need to have a large data to support your decision. So you can cut short, right? You can set the max depth, like when you create here, you can set the max depth equal to 2, right? So if you set the max depth equal to 2, what you got, you only get the shallow tree. If you make a prediction, right? For example, for this value, even though it's not a perfect split, it's going to answer you with the second class because the second class is the majority. And another one is the minimum sample split. So the minimum sample split is you tell you the minimum number of sample that you need before you split. So if I say minimum sample equal to 2, minimum sample split equal to 2, right? So it's going to split until I have 2, right? Minimum number of sample required to split internal node. So it's a fraction times number of split. Oh, okay. So I can specify the fraction or just a number. And then I can also specify the minimum sample leaf, right? So for right now, the sample leaf only have like 1 or 2. So if I say uh, minimum sample leaf to be 5, right? I need to have at least 5 data for my leaf. Um, what I get is a shallow tree. So it's gonna stop when we have 5, right? It will not split further, right? So it stop at 5. So these are the uh, parameter that you can set, right? You can also set minimum impurity decrease. This is when you know the actual value of the increase. Um, if I use entropy, let's try entropy. Uh, I have to be in the front. I think it's called criterion. Is it criterion? Yeah. So it's criterion. I can say criterion equal to entropy, right? And then for entropy, you actually come up with a similar tree, but it's gonna show you the entropy value of each of these one, right? So the perfect speed you have entropy 0, almost equal speed you have entropy to be like this one is more than 1. Why is it more than 1? Why this entropy is more than 1? Right? So we have 39, 40, 41, right? You have 3 terms. So let's use the entropy equation, right? This is entropy equation. Where is it? This one, right? So pi log pi and all the sum, right? So if we try to calculate the entropy by hand, um, so the entropy equal to, so it's minus, so you have 39, 40, 41, right? So it's 39 divided by 120, right? Times um, the log base 2 of 39 over 120 minus 40 divided by 20 and so on, right? Minus, I think it's 41, right? Okay. And then I have to import numpy so that I can use import numpy as np. So if you have more than 2 class, your entropy will go over 1, right? If you have more than 2 class, if you only have 2 class, right? For example, if you only have uh, this one would be like 80, 81. If it's equal split, almost equal split, let's say 59 and then 61, right? So this is like almost equal split. Then you have the number close to 1. But if you have like three classes, right, then your entropy will go more than 1. Right? We have last time like 39, 40, and then 41. Right? So entropy only go max to 1 when there are two classes. So just to let you know, because you will freak out why why is it more than 1? Like if it's two class, like you can see it's like very close to 1, right? And then you can save the model. I already showed you how to save the model last time. You import Pickle and then you can save the model file and then you can load it later. So that's all for the decision tree. Uh, so make sure that you submit the assignment by tonight. It should be in the Kaggle competition. If you submit on the last day, you have 10 chances, your last 10 chances of the day. Okay, if there is no question, I will see you again on January 5th. So there is no class next week, but after the new year on January 5th, then we come back. Okay? Okay, that's all.